Okay, so welcome. This is the, I imagine, 14th lecture. This is also a mistake. Probably copied without changing that. Okay. But let's have a summary first. What we have been looking at, it was the Bohr model for the hydrogen atom. And we got to the conclusion that it can be described, the energy states can be described as a discrete set of levels that actually follow this expression here. Let me spotlight, yes. Follow this expression here, and you can see that the ground state, the ground level for the electron is not within the nuclei, but is at minus 13.6 electron volts. This is an approximate way of looking at atoms, but actually when one does a more sophisticated model, I mean sophisticated, more accurate model in terms of the theoretical description, we get to a very similar, well, the same description for the energy levels, but a very similar description of the atom as a whole. But what I'm trying to actually recover from here is that, or get the idea is that essentially electrons in atoms have a discrete set of energy levels. Okay, so that's the bottom line that I want to take with me from last class and use it in what we are going to be seeing during this class. And actually, we're going to be doing two things. We're going to be looking at how does a laser work, okay, and what is the thermal emission that you can see of light when you heat up a certain body, okay? And those two things are lightly related, and I'm going to try to make the point how they are. But let's start with the idea of what a laser is. A laser is it's an acronym for the word that I have here. It's a light amplification by stimulated emission of radiation. Okay, so the LASER. Okay, so that's what a laser means. Okay, so for understanding how a laser means, I would like to actually consider a set of hypothetical atoms that has that have two energy levels, okay, and they are all these atoms, not two atoms, but many atoms. They are of this kind are contained in a transparent tube. Okay, so I have a transparent tube and I have a gas of atoms inside, and these atoms have two energy levels. So what will happen if I shine light on them with a frequency equal to the energy difference between the two states? We have the excited state here and the ground state. Okay, so that's sort of the situation that I would like you guys to consider. So the atoms are floating all over the place inside this tube. So what does it happen? So what happens is light is absorbed, meaning if do I have a diagram? No, I don't have a diagram. Okay, light is absorbed. The electrons inside the atoms, each one of the electrons inside the atom are promoted from the ground state A, yeah, we call this A, to an excited state which is A asterisk, something like this. So the excited state, it's metastable. What does metastable mean? Means it's nearly stable. So the atoms here are going to live in this excited state for a while, and then they're going to decay. So, and how will they decay? Well, the atoms decay by emitting a photon of energy equals to this difference in energy between the excited state and the ground state. So we send in radiation that lift the atoms up, and then we let them be there for a while, a very short time, and then they decay. Okay, so light is absorbed by the atoms at first, and then there is an emission, and that decay process is what we call a spontaneous emission. Yeah. In the case of the spontaneous emission, not both, everything, the direction, the phase, and the polarizations of the emitted photons are random. The only thing that is the same in this case is the difference in is the wavelength of the photon, because there are only two levels involved essentially. So the idea is the following then. So we have all these atoms in the system, and we shine light on them. Some of the atoms absorb radiation and get to the upper level, and after some time they decay again, emitting radiation, and the radiation is emitted in a spontaneous way. Okay. What I have just described is different from what I'm going to describe now. What I'm going to describe now is the situation of stimulated emission. Okay, what is stimulated emission? If we have enough atoms of this class, of the excited ones, and these atoms see in the nearby the presence, you can see that this guy doesn't have the option to actually absorb this particular wavelength, because it cannot do it, because the atom is already excited at the highest energy level. Okay, probably if the energy h nu is high enough, what will happen is that you can actually photo emit an electron from the excited atom. Okay, but what really happens, and which is a highly probable condition or situation, is that the atom will see the electromagnetic radiation of the nearby photon, will feel it, and will induce a transition. And the induced transition will have essentially the same frequency and phase as the and direction of the incoming photon. Essentially, what happened is, in this induced or stimulated process, the atom will finally decay to the ground state again, and at the end we will have two photons traveling in the same direction with a highly coherent phase. Okay, so the situation at first is just an excited atom and a photon, and at the end I have a non-excited atom and two photons. So this is different from the spontaneous emission. This is a process called stimulated emission, and the nature of the light is what is really counts. So the atoms are induced to decay by an incoming photon that is not absorbed. So the initial state was then an excited state and a single photon, and the final state is an atom in the ground state, A, no asterisk here, an asterisk here, and two photons with h nu. You can definitely see that if we can have, and then each one of the photons that have just emitted by this process can now do the same with another atom, and essentially you end up being in a sort of a chain reaction where all of the atoms that are excited will be induced to decay, and the light that will be emitted will be highly coherent and very intense, by the way. Okay, because of the multiplicative effect of the photons. Okay. So there is a note that is very important to actually consider here. That is that an energy level is different from a state of an atom. Okay. For example, in the drawing that I first drew here, even though this is not what we have just analyzed in the Bohr model, each one of these things represent a single state because it's just a single orbit. But when we do the quantum mechanics of this system, we find out that in this state, we actually can have the ground state we can build out of two states, because we have the possibility of having the spin of the electron, which plays a role. So we can have a ground state with spin up or spin down. There are different states. And something similar, and also including angular momentum, happens with this state at minus 3.4. So each one of these levels can have several states. So one thing is counting the energy levels or differentiating between energy levels. Another thing is just discovering that each one of these states can have several states. Each one of these levels can have several states within. Okay.
So if I'm getting it right, it's one level can have multiple states, but multiple states can only have one level, right?
Well,
for example, if you're looking at
it's not. It's only one way, because you can have many states, and the states could be distributed between this level and that level.
Okay, now I get it.
Okay, so essentially in this energy level here, I can have several states. That's what I'm saying. In this one too. That's what the real theory will actually show that. Okay, so that's the point. Let me go back now. That is subtlety of language, that it should be better. So one energy level of an atom can have several states. That is sort of the statement, and the number of states that it has is called degeneracy. Okay, so it could have, a degeneracy of 10 means that there are 10 states within a single energy level. Okay, that would mean. Yeah. So let's think about the number of excited atoms in a gas in thermal equilibrium, I don't know if we have seen this before in the previous sections of the course, meaning in physics 130 or something about thermodynamics, but you don't need to. You can now believe me. What I'm saying is the following statement: the population of the number of excited state of a particular energy level and not of an atom is equals to a constant times an exponential of the energy levels divided by the Boltzmann constant times the temperature. What is this thing? What is the meaning of this? It's, you can, let's say you have a system where the temperature is actually associated to the average energy of a system. So if you raise the temperature, you raise the energy of the system. And how do you do that in an atomic model? You actually have to start populating states which are above the ground level, or exactly that. So if you have a level up here, so some of the atoms in a system at a certain temperature will be populating a state up here. How many of them will do it? Well, the rule is the following. They will follow this. This is the law that they should follow. They exponentially grow as a function of the temperature. KBT is sort of a scale of temperature. This is a way of defining KB is what is known as the Boltzmann constant. KB times T is an energy scale. So this is an energy scale. And the energy scale actually is defined by the temperature, okay? So how does this work? That's why I graph it here. So let's say we have very low temperatures. Low temperature, look at the scale here, is 1 over kBT. This is the x-axis here, the horizontal axis is equal to that. So if the temperature is very low, this number is very high. So low temperature is pointing in that direction. So what happened with this as a function of 1 over kBT? This actually decays, okay? And it's non-different from 0, starting from 4 times E naught, okay? If it, you know, but when the energy scale is 4 times this, that's it. This is completely dead. This is almost 0, okay? And for higher temperatures, you start populating the states above. That's what it's saying. Low temperature is that direction, high temperature is this direction. It means that N will be substantially different from 0, okay? So that's the way the states are populated. And I would like to use this expression to find out in a gas at a very high temperature, how high, I don't know how high. No, I haven't done it here. I'm explaining. I chose 3,000 Kelvin for the reasons that it will become clear in a minute. But in this expression above, I have not defined all the terms here. You know, T is the absolute temperature in Kelvin. Okay, so this actually works only if T is absolute temperature. Okay, KB is the Boltzmann constant, and it's an obscene number as usually. It's 1.38 times 10 to the 23 joules per Kelvin. But why does it have to be joules? Because when I multiply this by temperature, it should give me an energy, and joules is the natural unit for measuring energy, but not at the atomic level, okay? So I only know one thing. Well, I know about the Planck constant. The h bar c is equal to 1973. And I also know that kBT at T equals 300 Kelvin, which is room temperature, okay? It's meaning a nice temperature of 20 Celsius in your room. And that is equal to 1/40th of an electron volt, okay? This is also a way of defining the same constant, but in terms of electron volts. It's approximate. For everything you do in the course, this is good enough, okay? So, and can have that in mind. So kBT, so the multiplication of the Boltzmann constant times the temperature when the temperature is 300 Kelvin is equal to 1/40th of an electron volt. That's a pretty low number compared to what we know about visible photons, because we are saying, you know, if a system like my hydrogen atom here, my happy hydrogen atom, where is it? Here, make a transition from here, from the state minus 1.5 to the 3.4, from here to here, it will emit a visible photon. Well, essentially anything that goes from here to here will emit a visible photon, but this particular transition will emit a visible photon, okay? And which is, you know, probably on the red side, okay, of the spectrum, yeah? But it's a difference of, let's say, you know, it's 1.7 electron volts or something, 1.8 electron volts between this guy and this guy, okay? So it's a photon of 1.8 electron volts. And so the idea that I will be able to populate this state by having this at a temperature of 300 Celsius is almost negligible, meaning why is that? Let me go back. Let me try to make the point now. I'm going to try to use this expression for doing that. So the number of excited states is proportional to this constant time the energy of the level, the excited state divided by kVt, and that I would like to actually divide by the numbers in the ground state, which is the same constant multiplied by this exponential. So in this way, I will have the ratio of numbers in the excited state by number of particles or atoms in the ground state. And if I do that for 300 Kelvin, I find out that this ratio, the number of excited atoms versus the number of atoms in the ground state, is a minuscule number that is 1.5 times 10 to the minus 4. What does it mean in practice? In practice means that 1 every 6,000 atoms in this bottle of gas at 3,000 K is actually in an excited state. So now I'm sending in a photon that has exactly the right energy to excite one atom, or from the ground state to the upper level, or actually induce a transition from the excited state to the ground state, because it has exactly the same energy. So it could actually be absorbed too. So, but there are no atoms in the excited states, because at 300 K, they 1 every 6,000 atoms is in the excited state. So the most likely thing that will happen is that my lonely photon inside this tube will find itself colliding with an atom in the ground state, and hence being absorbed. That's exactly what will happen, okay? So if that's the case, you know, this number is just too very small to get the process of stimulated emission going on. So in order to get the laser effect, the light amplification by stimulated emission, we need to invert the population. What do you mean by inverting the population? Meaning, this is the model that I have, okay? The model that I have now is I have plenty of atoms in the ground state. This is thermally excited, meaning, and I have few, because this difference in energy between this state and this state is several electron volts. And even at temperatures as high as 3,000 Kelvin for that gas, which is, you know, everything will be melted at that temperature. These guys over here are 1, when down here I have 6,000. So that's sort of is the ratio. So essentially, this photon here, what will happen to this photon here that has the right energy to induce this transition will be absorbed by one of these guys, and we pull one guy. So now in a section of 2, there will be 2 atoms instead of 1 every 6,000. Big deal, nothing happened with that. Really what I need to do to actually induce this light amplification is that, look what I did. I used the program to actually copy this and put it up here, and copy this and put it down here. So I literally, what I've done graphically is invert the population. I need to have all the excited atoms in the upper state and very few in the ground state. Clearly, this situation is not an equilibrium situation. The equilibrium situation is the one that I've just described. So I have to manage to handle the system in a way that I could sort of punch it, so all the atoms will be in the excited state. If I have this situation, the most likely outcome of this atom is that it will induce what? It will induce a stimulated emission of another of these atoms right here. You will never see these guys. You will only see this guy. And when you see these guys, what it will happen to them, it will induce a transition to the lower state. So, and the other guy will also induce a transition. So I will have a cascade of coherent photons being emitted as the relaxation process about getting from this state to this state occurs, okay? So many excited atoms, stimulated emission is very likely. So the rate of stimulated emission is much, much larger than the rate of absorption in this case. So in order for a laser to work, this is exactly the picture that I should try to get. Okay, otherwise, the system is not going to work. So this is a nice summary. What we have here, we have this two-level system, and they are all the atoms in this case are in the ground state. And so this three graphs essentially summarizes everything that I've just said. So the photons that are coming from the outside, in this case, it doesn't really matter. I have the photon of the right frequency inside the tube. What will happen with that? Most of the guys are going to be in the ground state. So since all the atoms are in the ground state, they are going to be pulled up to the excited state. Okay. So what will happen then? There will be very sparse, very distant away atoms. Not very many atoms are going to be in the excited state, okay? Because they will decay. How will decay? Well, they will decay by spontaneous emission. This photon is not going to be very likely that we find another atom in a situation like this, because I only have a very few atoms in the excited state, okay? So this spontaneous emission will produce radiation with the same frequency for all the atoms in the decay process, but the direction is not going to be the same, and the phase is not going to be the same either, okay? Polarization is not going to be the same either, okay? The situation that I want to produce is the one that I have here, so that almost all the atoms are in the excited state, and I put a bunch of photons in with the right frequency. And what I do is I actually stimulate them to decay to the ground state by emitting a photon that is in phase, essentially coherent with the incident photon, okay? So this is the phenomena that I need to actually create a laser. That's a laser, essentially, okay? So how do we make something like this happen? You need some sort of engineering, and you need to select a system that will actually work like this. So then again, here I have a model system that it has, instead of 2, it has 3 energy levels. 1 ground state, and 3 excited states. So this is the ground state, and I have this excited state, and this excited state. And also the lifetime, meaning, what is the lifetime? The lifetime is, I pick one of the electrons from here and put it up here. I'm sorry. Pick one of the atoms and raise it to the excited state E1. So essentially, in this diagram here, we mean grabbing this guy and putting it up here. How long will it last there? Well, there's phenomena that actually induce this this state to decay. And if the lifetime of this state is very short, it means it will stay here for a very short time. How long will it stay? In average, T1 seconds. Okay, and I would like the time of residence of the atom in this excited state to be T1, to be very short. This guy the T2, the resonance in this excited, I want it to be long, okay? And the resonance in this excited state here, T3, I want it to be short. So typically these values, the T long is of the order of milliseconds, and the T short is 10 to the minus 5, the T long. That's sort of a good set of numbers to actually have a laser action in this in this kind of system. Okay. So the laser action or the amplification is induced between the two central levels, between the levels 2 and level 1. Okay. And let me explain how it works. Okay. The idea is that we actually induce some sort of an electrical discharge inside the gas. So we have this here is supposed to mean the light. Okay, there's no tube here. The tube is only the glass envelope here, and there's a mirror here that is 100% reflective in this side, and there's a mirror here that reflects almost 95% of whatever comes in. So these two mirrors are very well aligned in such a way that a photon that will bounce here could be bouncing back and forth here until it finds an atom inside the tube. Okay, and these guys are actually making it through because this is a transparent glass essentially, and how do we excite the atoms? We have a metal thing here, and we put a power supply and a pulse of high voltage. We put a pulse of high voltage, create a discharge here, and the discharge, what it will do? The discharge, what it will do, it will bring the atoms that are in the ground state, and it will populate atoms here, here, and here. It doesn't really matter in every place. Okay. So why would we get laser amplification if we do something like that? Well, you know, the explanation is kind of here. Okay, so this is the situation that we have inside the tube with the atoms, and all the atoms are essentially in the ground state. That we saw that 1 every 6,000 is up here. We can, you know, throw it away, you know, because it's from the practical point of view, all the atoms will be here. We just boom, get them a high voltage pulse that creates a discharge inside the gas. And what does that do? Well, you get everything. Everything gets excited. All the states get populated with different numbers. You know, the energy of the pulse is so big that it doesn't really matter. Some of the guys will go here. Some of the guys will go here. Some of the guys will go here. And many of the atoms will actually stay in the ground state, because it really depends on geometrical aspect, how efficient the excitation process is within the gas discharge. Okay, but you can see that this is very sort of conspicuous here, because we have 3 atoms here, 3 atoms here, and 3 atoms here. So this is sort of the model for after the pumping. Okay, we sort of exciting of this chain of atoms, 9 atoms up, fairly legitimate. But what happened next? What happened next is that these guys will follow very rapidly by different mechanisms. This could be collisions, for example, from here to here, or it can be optical. Okay, they will, but this will be this is a short-lived state, and this is the T3 is almost equal to T1. So it means that this guy is going to be depopulated very rapidly. And some of the atoms that were here will decay to the ground state, and others will decay to this excited state here. None of this, since the time is very short, this is about 10 to the minus 8 seconds, which is the decay length of E3 and E1. E3 and E1 will be empty. But since these guys here at the E2 level it has a much longer lifetime, wow, what did we get? Get here essentially the inversion of the population. Here we have atoms in this state, no atoms here. Essentially population, complete population inversion, meaning everything is in here. So if for some instance there is a photon, what would be some instant? Some of these guys decay down here and produce a photon of what energy? E2 minus E1 flying inside the tube. What will happen with these guys? Well, these guys will be induced to actually decay to this level through what? Essentially the emission of radiation. And but it will be a stimulated emission, okay? So this guy will decay here, but this guy will produce a photon, and then there will be two photons after this guy. There will be, you know, another photon after this guy. So essentially, it will be a cascade of photons, all of them coherent, with the same frequency and with the same polarization. This is essentially how lasers work. This is what you have seen here is sort of the explanation for a gas laser. Okay, there are lasers that actually slightly different. They work. The one that there is in the supermarket, the one that to read the barcodes, it's a solid state laser. The one that you know point to the transparencies to in a presentation. It's also a solid state laser. And the lasing effect there is actually obtained by states which the electrons inside the material can access just by moving around. Okay, so you need to supply energy continuously, and the electrons will be cascading in phase essentially, and producing the light. So, but that's a very, I don't want to get into the details of how the solid state laser work, because the details with the materials are a bit more complicated. But you know, the idea here is that one photon of light, let me get here, one photon of light here with the right frequency for a transition between these two can induce a cascade of transition of all these guys emitting a very coherent pulse. Let's say, you know, the frequency of the laser is operated at, you know, 5 times 10 to the minus 3 milliseconds. Essentially, these guys will all be gone after the first light pulse, and then I will excite everything and we start the process again. So from the point of view of the light, you will see almost a continuous light because you cannot see the flickering of the gaze laser at that frequency if it's a fraction of a millisecond. Okay, so that's the way we expect this thing to work. This is sort of the geometrical aspect of how the gas laser should be implemented. Okay, here we produce the energy for the excitation, and then we produce the light in the output. This is a typical thing with the helium neon lasers. That it was the beginning of the gas phase lasers. Let me switch gear now to something that you guys are actually very familiar with, if you like science fiction movies, at least, you know. Well, or if you have been in a shop where the guys are actually warming up a piece of metal to actually try to work it out, you can see that when they put the piece of metal in the fire, that piece of metal comes out being red at the end, or something like that, or almost white, depending on the temperature. That you can actually raise the actual temperature of the piece of material. Okay, so the type of spectra that we were seeing before, it's a line spectra, because it has to do with energy levels that are discrete in a system. Okay, you can immediately ask me, if you know where I'm going, if I actually warm up the atoms enough, why would they produce a continuous spectra if I have just told you that the atoms have discrete energy levels? So they should look discrete then, And no, because the difference in the two systems is that in one case I had an isolated atom, okay, with discrete levels that interact with other atoms only through the radiation in the media, okay? So it retains the pristine thing of the singular energy level. But if the interaction between the atoms is very strong, meaning they are close by each other, the radiation emitted then is a continuous spectrum. And the analogy that you can make, well, you can have a very good resonator when it's isolated, but if you bunch them up all together in a small region of space, you see, apart from the actual wave of each one of them, you'll see the interaction of the whole mass of material. Okay, so that is essentially what goes on here. The interaction between atoms becomes very relevant and becomes the dominant effect, and that will induce the emission of radiation in a continuous form. This is essentially what I have here. So this is the characteristic emission curve for a fixed temperature of a material. This is a fixed temperature, so the intensity you can actually depict here as a function of lambda or something like that. So when lambda is very short, meaning high energy photons, there are almost no photons being emitted. Then there is a maximum, and they decay for long wavelength. Okay, this is long wavelength, this direction. So this small I versus lambda is what is called the spectral intensity of the light. Okay, if I add up all the contributions for all the lambdas here, meaning the area under this curve here, what I get essentially is the total intensity emitted by an object which is at a certain fixed temperature. Okay, and well, I is then the intensity of the radiation emitted by a body of a constant temperature. What is I? I is measured in watt per meter square. That is the intensity. Okay, so you have a surface that is at a certain temperature, and that surface emits radiation with nothing. This is the I that actually quantifies that. It usually has a spectral distribution like this. This is the spectral intensity distribution, which is something 0 here and 0 at long wavelength, and it has a maximum in between. Okay, so there is something that is called an ideal radiator, and it's called like that because people. What I have just shown you here, this is an experimental fact, and then people, scientists, good scientists, try to make models to describe this thing in a way. Okay, and what we can do is describe an ideal radiator, a black body, and the radiation of all wavelengths is always absorbed and emitted by the subject, meaning that's why it looks like black. Something that looks black, and that's why it's called black body. Something that looks black is something that when you shine it with light, there's no light that bounces back. Okay, so what does it mean? It means that the object is actually absorbing that light. So you see absence of light so that's why it's called black body radiation. Radiation is actually emitted But one property of this object is that it actually absorbs all the incident light independent of the wavelength. Okay. This is also something empirical. If you actually do this integral of the spectral radiation on all the wavelengths possible between 0 and infinity, you actually find out that the actual intensity, the emitted intensity, is equal to a constant of this ideal black body thing times t to the 4th power. This T here, again, is absolute temperature. So if something is at 0 temperature, the emission is very low. And as soon as the temperatures start to grow, and you can see that this is a very steep function of temperature, okay? You will start to see radiation emitted. This is a type of thing that you see when you heat up a piece of metal. And you see this red color that comes out of warming up the metal. The intensity emitted is proportional, the total intensity emitted is proportional to T to the 4th. The apparent color of it has to do with where this intensity maximum is. So this graph is for a fixed temperature. So if you raise the temperature, you actually move this maximum to a smaller wavelength. Smaller wavelength means higher frequency of the emitted photons, okay? So warming up, it means that the color, the dominant color will be the characteristic color of the maximum emission, okay? So when the color moves from red to yellow, it means that going to yellow, the actual object is much warmer, okay? And if after yellow it goes to green, don't even get close, because that is really, really warm, okay? Okay. So this is called the Stefan Boltzmann law, and obviously this thing here is called the Stefan Boltzmann constant for that reason. So and this is you can actually try to fit it. Every object, independent of the nature, will actually have an intensity that will be very much a function of T to the 4th, but the emissivity will be a bit different, meaning the amount of the intensity that come out is not going to be a constant value. It will have some sort of a modifying factor here that will depend on the material. But for an ideal radiator, a black body radiator, this is a value of sigma, and sigma has a real number here, is 5.67 × 10⁻8 watt per meter square per Kelvin to the 4th, which is right, because if you look at this expression, this is intensity with watt per meter squared. That's the radiation that comes out of the body, of the surface of the body. It has to do with the Stefan Boltzmann constant times the temperature to the 4th. So it has to have a cancellating factor of 10 to the 4th to actually provide the intensity here. So I is the power emitted by the surface area in watt times meter square. Okay, so this is the emitted intensity. I is the power emitted by the surface by unit of wavelength. So it's watt divided by meters cubed. How do we get that? Well, let's go back to this expression here. See, you have to multiply I by a length. D lambda is a length. The small I by a length will give you a I, which is watt per meter square. So this guy here should be watt by meters cubed, okay? So that's the difference between the big I and the little I. Unfortunately, the book doesn't make this difference so obvious. It writes I, the little I, as the big I as a function of lambda. So it could be ambiguous there. I rather use this notation, okay? And this is a very interesting aspect here. As bright as the sun is, its radiation intensity corresponds to a black body of 5,800 Kelvin, okay? So this is if this is a universal constant, you can have an apparent temperature of the surface of the sun that provides the actual intensity as a function of lambda. So this curve over here, there's a funny thing about these curves. You know, this is measured for a fixed t, okay? But if I scale this value, the value of the maximum appropriately, all of the curves that I can find, they will follow the same functional expression, okay? So if I measure the spectral intensity of the emitted light as a function of lambda, they have the same functional form, which is a very nice thing because it will mean that independent of the temperature, I can explain this value with the same with the same expression or the same theory, okay? So there's another interesting evidence here. This is also this is called Wien's law. I should have write it. W-I-E-N law that shows how the wavelength for the maximum intensity shifts with temperature. And the product of the wavelength for the maximum intensity times the temperature goes like that, goes like a constant. So when you increase the temperature, you decrease the actual wavelength, because since this is a constant, you divide by the temperature here, the wavelength of the maximum increases, okay? So let me go here again to my graph. This thing, as I mentioned before, as you increase, this is for a fixed temperature. If you increase the temperature, this value will move here, and then we move there as the temperature increase, okay? How does it change that maximum value? Well, it's exactly that one, okay? And this is what we call Wien's law, okay? And it's also an empirical number that is 2.9 × 10⁻³ watt. This should have the same units as this, meters times Kelvin, okay? You can change the wavelength and change the units, but it is important to know that that is the, yeah. So in optical terms, the apparent color of a hot object moves from the red, I've already said that, red, which is rather cold, which is the cooler thing that you will see, to yellow, which is hotter, to green, that is even hotter than the yellow, okay? So when you move into the rainbow colors, into smaller wavelength, means higher frequencies, as the temperature increases, okay? Okay, this is the theoretical description of this phenomena. This is very qualitative. This is not an intention that you will learn how to actually make a deduction of this. This you have to internalize as a fact of life at this point. You know, going into the detail is a little beyond of what we're interested that you guys learn from this topic, okay? You should know the results, but not the deduction, actually. So this is the theoretical description, which is due to Lord Rayleigh, that produced a model that you know, that the intensity of lambda is equal to something that goes like this. Well, it's proportional to the temperature, but inversely proportional to lambda to the 4th. Wow. But it doesn't look like you know, the original thing, you know? The original thing looks like this. It looks like it dies for big lambda, essentially as the Rayleigh curve shows. But here, when lambda goes to 0, this thing goes to 0, but this other expression, the Rayleigh relation actually diverges with lambda, okay? And this was really a problem on in theory. They knew that, you know, that they had a way of calculating this using what they know about physics at the time, and they had this trauma, you know, this trauma that you know, things didn't work out. They didn't have a nice explanation. They were facing the situation where they needed new physics to actually give this explanation. Actually, I'm actually reversing all the arguments. I've already told you the solution to this problem, okay? Because we started with the fact that with the things that we know. What are the things we know? We know that photons, the light is constituted by photons, and photons contain discrete amount of energy. Each photon contains a discrete amount of energy. If you have a big number of photons, it means a big number of particles, and so this is different at the things they were considering. They were considering a model based on a continuous radiation, okay? And the model of continuous radiation, of actually considering that they have a continuous distribution of atomic oscillators, and the energy of the system is evenly distributing, you know, 1 k bar t, one unit of energy, which is the Boltzmann constant times the temperature, in each degree of freedom that the system has, and that's, you know, a good classical mechanical argument. It produces this thing that doesn't fit with the actual experiment. So what was the solution? Well, you know the solution already. The solution already is that light is quantized, okay? And let me try to make a point why the quantization of light makes this whole difference, okay? So the guy that actually came with this was not Einstein, was actually Planck. But when he did this calculation, he actually said, look, this is the only way that I can, you know, do it to fit the data. And actually don't believe very much the model that I'm actually doing, because, you know, I have to take only certain frequencies that are allowed, and I have no reason whatsoever to claim that certain frequencies are allowed. Certain frequency for the atomic oscillators are allowed, and others are not. And well, you know, he was facing exactly that. He was facing the fact that light was quantized, and he didn't want to believe that, even though using the quantization of light produced the right model. Okay. So the key difference between Rayleigh and Planck's model is that the energy is not distributed evenly among the different modes. In the case of the discrete energy levels, meaning the quantized oscillation, the occupancy of a certain oscillator with frequency n h bar omega is equal to, with the same Boltzmann argument, is equals to a constant times e to the exponent of the energy divided by kVt, okay? So if this energy here is over the order of visible light, which is the case at very high temperatures, this is a very, you know, this is a negative exponent factor, and kVt is a small number, and h bar omega times n is a high number. So the occupation level of this of these guys is actually reduced very much so. So the model proposed by Rayleigh of evenly distributing the energy about all the modes of the system is not valid, okay? Because the occupation number, if the energy is discrete, is very limited, okay? So the radiation is emitted by transition between levels of the atomic oscillators. That's what it is, okay? So let's see if I have a system that is let's say I have something at a certain temperature, and I have two energy levels with an excited state, with the ground state and a not here, and an excited state here at HF, okay, a certain frequency. So if this difference between this guy and this guy is small, then the thermal excitation is possible, okay? So this will be, very likely excited state. But if this energy is very high compared to the actual thermal excitation energy, what is the thermal excitation energy? The thermal excitation energy is KB times T. That is the actual scale of energies when you are speaking about temperature. And you have to compare the energy levels of the system with the thermal excitation energy, which is KBT. So in this case, this could be exponentially reduced with respect to this because this number is very big. So there will be very little excitations of high energy vibrations like this, meaning the number of photons that will come out at high energy will be very low if this energy is too high, which is exactly, what you get in the experimental value. Very low energies at very high frequency. This is a high frequency, okay? So that this is what it, and remember the Rayleigh theory goes like that, and when it gets here, it keeps going up, keeps going up, and keeps going up. And to correct for that, we need to introduce the fact that the light is actually quantized as photons, and when you do that, you don't get to excite as many states, okay? It goes down. This is exactly the reason why we get a model like that. And again, I'm not gonna, give you the Planck solution for this thing, but the expression that I have for I the lambda, the small I, is the expression that I have here. And it involves the Planck constant, not strangely enough. He didn't call it like that. He called it a constant, by the way. So we, all the rest of the physicists after him, or not me, guys much older and much better physicists, call it the Planck's constant. And and it's the same Planck constant that appears in the HF of the difference in of the wavelength, okay? So, and this is the first time somebody, induce or imply that radiation was quantized. So this is the expression that he get here a lambda to the fifth. He get here hc divided by lambda. What is that? That is the energy. Hc divided by lambda is the energy of a particular photon, okay? Divided by kBt. This is the excitation energy. And well, it doesn't have the negative sign here because this is below. That's why, okay? So this is the right expression. -1, and you'll see why in a minute. Temp T is the absolute temperature. I don't want you guys to learn how to I'm not going to require that you learn how to deduct this thing, but I really would like you to use this thing in a positive way. I mean, this is a result. Now we know the intensity as a function of lambda, and we know that there is a theory behind it that has to do with the fact that light is quantized, is made out of photons, okay? So the interesting thing is that you can actually find if you actually plot this thing, it will look very much the same as the graph that I showed you before, okay? The experimental graph that I showed you before, and you can see that you can find where this thing is a maximum. This thing is a maximum when it will be zero. The derivative of I the lambda with respect to lambda will be zero when evaluated at lambda maximum. Okay, so we're finding what is the value of lambda maximum, and the text propose a way of doing this, which is the standard way of doing this, and the solution is the one that I'm showing here, or essentially HC divided by lambda m, lambda maximum, is the energy of the maximum intensity, and the energy of the maximum intensity for a particular temperature is equal 5 times the typical thermal excitation energy. So this is getting this guy going here and this guy going here. So 5 times the typical excitation energy is the energy for the maximum intensity of I of lambda. Okay. So guys, this is going to be a homework. The homework is follow the text and prove the relation one. Prove that this is true. Okay, and it's a very simple thing once you know how to do it. Otherwise, it could be very cumbersome. It can also be shown that if you integrate this expression, what expression? This expression here, if you integrate this as a function of lambda, for all the possible lambdas, you get something that goes like t to the 4th. Wouldn't that be nice? So essentially, this Stefan Boltzmann constant that I have in front here, I can actually have a theory way of predicting how much what is the value of it. Okay, so the value of this is this, and an actual if you measure this, it probably in a piece of copper is different than a piece of gold, and it's different than in a piece of silver. They all depend on 10 to the 4th, but the actual value in front here is slightly different. So people introduce what is called an emissivity here. It's an epsilon factor in front that actually compares the actual intensity emitted with the perfect black body radiator, which is the expression that has been shown here to be valued. Okay, so there is this can be used universally, and this has been shown to be correct in many instances. Note for the sun, for example, that the apparent temperature of the surface is 580 Kelvin, and the maximum frequency is produced at 5,000 angstrom. You know what 5,000 angstroms is? Well, I've told you many times in this course already. That is exactly the color green. So there's no surprise that humans have been adapted over the millennia, actually from the beginnings. I don't know what is the evidence of how long several million years, several thousand years, probably a millennia or something like that, that the man has been working on Earth, and different species than us, and the human eye has the highest sensitivity exactly at that color. Well, that's adaptation. And this is why, the trees are green, because they collect very efficiently the light from the sun, which has a maximum at that particular energy. So this thing of black body radiation has to do with that, with emission and absorption of radiation, and it does it in a continuum spectrum. So what I've told you today is the two sort of sides of the coin. And both of them are actually linked by the fact that light is quantized. To get the right explanation for a continuous spectra, we need to go to physics that make use of the fact that light is quantized. So there's a nice symmetry here, and both the laser and the continuous spectra can both be explained by photons. Okay, so So this is the main message for today. There's not too much algebra here, whatnot, but you have to read this for a while. The actual finding out what the expressions are, it's a bit more cumbersome that what we expect you guys to handle in this course. Okay. So this is the lecture for today, guys, and I guess I'm right on time. Okay. So enjoy the weekend and see you next Tuesday if everything goes well. Okay.
All right. Thank you very much. Have a great day.
Okay. Same to you. Enjoy it. Ciao.